So, learning objectives in today's lecture, we want to understand why high performance enclosures are necessary. If we don't already, I feel like you guys probably, a lot of you have a good idea as why they're important, and the implications of having a high performance building versus a low performance. We want to explain how climate is categorized in the ASHRAE climate zones. We are going to discuss where energy is used or consumed in buildings. We want to remember the priorities for conserving energy in homes and discuss envelope loads versus internal solar gains. We'll get more into that in later lectures. We'll see how our time goes today, though. Okay, so here we're looking at a chart on operational energy and how it compares to operating, ongoing embodied, and initial embodied. Okay, so embodied energy versus operational energy for a building. So we need to understand energy performance over the life of the buildings that we're designing, right? It's not just how much energy goes into it when we build it and how much energy is being used in sort of the operation of the building. There's more to it than that. This graph gives us an idea of how buildings have performed in the past. This is taken from the book. It's from a 1996 study by Cole and Kernan. The purple line you have here is initial embodied energy. So that's energy that goes into things like making Portland cement for concrete, or energy that goes into harvesting timber and transporting it to the timber mill and then kiln drying the timber, so on and so forth. So researchers have tried to track all of this stuff down and get an idea of how much energy it takes to produce materials and put them together. So the green line is ongoing embodied energy. And this is related to upkeep and maintenance and other general things like that. And as you can see, it gradually increases over time. The red line is operating energy. And so this starts at 0, and you can see it increases pretty rapidly over time. And the amount of energy we have to put into our buildings to make them comfortable and keep them healthy, and a healthy environment for us to work and sort of just be in most of the time, far exceeds the amount of energy that goes into materials and putting together the building and stuff like that. With that being said, this data is from 1996 and probably represents a building with lower performance values than what we think of now as sort of benchmark, or a building that's sort of standard. So if we were to look at a modern building, the overall energy might be a little bit higher. With the embodied energy is going to go up when we put more high performance materials in our building. When we put more effort and detail into how we construct our buildings, that energy is going to go up. But the slope of the operating energy curve is going to be much lower than the building charted here. So, we might start a little bit higher, but it's going to be lower over time. So that's one of the big problems in the commercial environment, is upfront costs versus life cycle costs. When you have developers looking at, the bottom line, the bottom dollar, and then they're just turning around in 5 years and selling that building, when they're going to make upgrades to the performance aspects of the building, they tend to not look at long-term performance upgrades. They tend to look at things that have quick paybacks, and it depends on sort of what sector you're looking at, but that's something that's pretty common in the construction industry. So like I said, that the operational energy is still going to be a lot more than the embodied, but over time it's not gonna go up as high as a lower performance building. So we're focusing on minimizing our need for operational energy, because our operational energy is the majority of the energy used in construction and in the lifetime of a building. I think that's one of your quiz questions. Do you guys have the quizzes downloaded? Did you guys get those? Okay, cool. So, like I said, operational energy is the majority of energy used out of the total energy that goes into a building when you're looking at initial embodied, ongoing embodied, and operational energy. And a big portion of this operational energy can be accounted for in our HVAC systems. I think there's another quiz question. So the HVAC operation and system design is going to depend heavily on what climate you're in. When you have engineers designing these systems, a good engineer is going to look at the temperature, it's going to look at the climate in which the building is going to be operating, right? They're going to be looking at the temperature, at the daylight, at wind speed, at rain, clouds, etc., to get a firm grasp on the conditions that the building is going to be operating under. There's historical data, weather data from various years, and they can look at that and get an idea of what to expect. So this process takes a lot of time and effort to carry out effectively in order to come up with a meaningful design based off of this stuff. So for something like the building code and our construction assemblies, we need to have buildings that are built according to climatic conditions, according to the environment in which they're built and under which they're going to be operating. You know, and this needs to be repeatable. Every building is built based around the needs and the environment that it's going to be in, right? Not every design is going to work in every climate, but we also want to have a method that's not super time consuming for our building design. You know, given how much time and effort goes into building and designing the systems and stuff like that, we need to cut down on that as much as possible. So, and like I said, it needs to be repeatable and it needs to be accurate. So we've got different methods for quantitatively representing the climate with temperature, etc., taken into consideration. This is called heating degree days. I talked about this a little bit before, and we're gonna look at what heating degree days are today. So ASHRAE has taken this and used this stuff and come up with climate zones. And your climate zones take things into consideration like temperature, humidity, precipitation, etc. The ICC, the International Code Council, and a lot of states will use this map to represent building code requirements. They built boundaries on this map based on counties, and then the counties have the authority to modify codes based on their environment and as they see fit, based on what's practical, stuff like that. Excuse me. This is an easy way to create building codes that are enforceable, something that is, you know, repeatable, everybody's held to the same standard, and it's enforceable. They can, you know, they have building codes in place. You have to adhere to the building codes. The inspector comes out. If you're not up to code, they make you change it. They don't let you continue on with your construction, so on and so forth. So, you know, these building codes are based around the climate conditions, the environmental conditions that your building is going to be operating in. North Carolina has 3 different climate zones in it. You see down here, they're color coded. We've got 3, 4, and 5 in North Carolina. So the low numbers on this map, like 1, and then it goes up to 7, and then you get into Canada and it goes even higher. But the low numbers on this map represent warmer climates. The higher numbers represent colder climates, and then it's also split into, I guess it would help if I was drawing on this. It's also split by humidity levels. So here you have moist, A is moist, B is dry, and then C is marine, where you have, you know, super humid areas where there's a lot of clouds, fog, high humidity, stuff like that, especially in the winter time. in the Pacific Northwest, stuff like that. So again, numbers are associated with temperature. There's another quiz question. Letters are associated with humidity levels. So as the climate changes, we need to update our map, this climate zone map. The most recent update was in 2016. This stuff here is pulled from the National Fenestration Ratings Council slideshow. So thanks to them for this. This indicates where ASHRAE has made changes based on current climate data versus the original climate data that was used when this map was made. So you see we've got some big changes happening here in North Carolina in particular. The new map that was made will not be recognized by the International Code Council, the ICC, until 2021. And remember, the ICC create the model building code. The states sort of take their direction on their codes based off of the model building code. So if you'll look at the difference in the zones in North Carolina, more of North Carolina is going from climate zone 4 to 3. North Carolina is warming up. So you can see that big change here in this area going from 4 to 3, warming up. So that's, you know, that's going to have some implications on construction assemblies and stuff like that in the code. And I've said this before, I think, and I'm sure a lot of you are aware of this, changes happen slowly in the building industry. You know, where we are now, it's taken a while for us to get where we are now. And so, you know, how quickly the code can get caught up with this stuff, you know, is yet to be seen. But, you know, where the state's warming up, you're going to have differences in things like system sizing and stuff like that, and insulation levels. You won't need quite as much insulation, stuff like that. So we'll see how quickly that happens. And like I said, it's not going to be this map's not going to be recognized until 2021. So and again, in North Carolina, there are 3 zones, 3, 4, and 5. So good to know what climate zones are in our state, especially when you're in the building industry. So to have an idea of what zone some of the major cities are in, Charlotte's in zone 3, Raleigh is in 4, Boone is in 5, Wilmington is 3, warm humid. So you know, in the warm humid zones in the building code, there are notes that say if you're below the warm humid line, that you have different requirements for things like basement insulation and stuff like that. So a little bit about heating degree days and sort of how that works. So I'm going to try to draw this, and hopefully it won't be terrible and a giant failure, but like I said, just bear with me. So you got your house. We have a temperature set point inside of our house, right, where we like it to be comfortable. And you know, heating degree days comes back to your house. So this is how they decide what climate zone your county is in, and they do this by using heating degree days. So it's cold outside, it's winter. Here's your house. You've got a heater in your attic. Hopefully it's in conditioned space. Whenever you guys are designing homes in the future, don't ever put your HVAC system outside of conditioned space unless you've done something to make sure that you're not going to be causing undue loads on your HVAC system. So if you're trying to cool your house and your thermal envelope stops at your ceiling, and your roof deck is 200 degrees and it's 180 degrees in your attic, and your HVAC system is up there, and you're trying to pump cold air into your house, but you've got, you know, cold ducts in your attic, and your attic's vented, and you've got warm humid air up there, your ducts are going to be sweating, and there's going to be a load, you know, you're going to be having heat gain into your ductwork from your hot attic. So, you know, it's a good practice to put your HVAC systems inside of your thermal envelope, just as an aside. So you've got your heater in your attic, it's pumping warm air. You want it to be about 68 degrees Fahrenheit inside your house, right? So we have this thing called the balance point. So the heater is going to kick on at some temperature outside to keep your house at 68 degrees. When it's cold outside, we're losing heat through the envelope, right? So, you know, energy moves from higher concentrations to lower concentrations. The pressure inside your house is going to be higher than the pressure outside. So that energy inside of your house, whatever the little dots there are your energy, it's going to want to move outside of your envelope, right? It's going to want to move to the exterior of your house. And the higher the temperature difference, sort of the more energy is going to be transferred. So again, the heater is going to kick on at some temperature outside to try to keep it 68 degrees in your house. You've got heat moving through the envelope. So when the heater kicks on, it's pumping heat back into your house, trying to keep it 68 degrees. So this temperature outside, we're going to call the temperature balance point. Okay, whatever temperature outside it happens to be that makes your heater kick on, that's our balance point. So TBP is our balance point. So at this outdoor temperature, we have to start spending money to make the interior of our house comfortable, right? This balance point is a number we use to keep track of when our heater is going to be on and running, and we're going to be paying for energy. For a typical building from the 80s and 90s, the normal balance point is about 65 degrees. So it's cooler than your set point inside of your house. You've got people that are giving off heat. So there are heat gains inside of your house that are you know, adding heat to your house on top of your heater. You've got, you know, your television gives off heat, your refrigerator gives off heat. So when it's 65 degrees outside, when it drops below that temperature, when it hits 65 degrees outside, that's when you're going to need to add heat to your house. So if we have, say we have a really high performance building that's insulated really well, that's going to change things. So we've got our high performance building, and it's got, you know, super thick insulation. They spent some money on the upfront cost to lower the cost of operational energy and to lower the need for operational energy. So where you're losing a ton of heat across this typical envelope, you're only losing a little bit across the envelope of your high performance building. So, you know, when you have high levels of air sealing, you're not going to lose as much heat through that. And you have higher insulation, there's a higher resistance to heat flow across your envelope, right? So, you know, the balance point for this building could be 55 degrees Fahrenheit or something like that. But a typical house, the balance point's 65. And that's what we're basing our heating degree days off of. As we've talked about in conductive heat flow and convective heat flow equations, we have a delta T, or a temperature difference. Okay, so we want to quantify how much energy our heater is going to be using to keep our building comfortable based on our climate. So if we use our heat flow equation, we can manipulate our equation to help us do this. So if we use the average temperature difference for 1 hour, we multiply by an hour, we're trying to get how much energy our heater is using based on the balance point from the house. So I've got Q dot area over R value times our temperature difference times 1 hour. And so we're going to change this. We're looking for total energy, right? So we're looking for BTUs. So this is, remember, the dot indicates that we have a flow rate, right? It's not total energy, it's flow rate of energy. So, you know, instantaneous rate. So we're just going to have Q, total energy, equals area over the R value times delta T times 1 hour. The difference being our delta T, goof that up. Our delta T in this scenario is going to be our balance point. We're trying to see when our heater is going to be running, how much energy it's going to be using. So our delta T, when our heater runs, is at the balance point or below. So when we hit 65 degrees outside, minus the average outside temperature. So that's going to be our delta T in this scenario. Oops. So if we're trying to get how much energy our heater is using, we can add up all the energy for every single hour of the year. And that's what we're doing with heating degree days. So in this equation, we're going to do the summation of, we're doing the summation of this equation. So the sum of area over R value times the temperature balance point minus the temperature average hourly out times 1 hour. So in practice, this equation looks like, so our heating degree days, we're taking the sum, that means we're summing balance point minus temperature out, average daily times 1 day. So we're doing it at time step 1. We're doing this for 365 days a year. So, you know, if the thing is, we're trying to look at heating energy. So we don't want to look at temperatures that are higher than our balance point, right? So if our balance point temperature is greater, or no, excuse me. If our outdoor air temperature, OA, outdoor air, is greater than our temperature balance point, then we're going to say this is equal to 0. So we're not taking into consideration negative numbers. That would be for cooling degree days. So, you know, and if we're looking at this stuff on an hourly scale, it's going to be doing the same thing. It's going to look a little bit different. So heating degree days is going to be sum of 8,760 hours in a year. You're still looking at the first time step. And this is going to be times temperature balance point minus temperature outdoor air average times 1 day over 24 hours per day. Your hours and stuff, when you're looking at the R value and all that stuff all cancels out. It's doing the same thing. So you might see it like that sometimes, depending on, you know, some of you guys may never look at this stuff again, but this stuff is good to know, and especially if you're interested in systems or energy modeling or anything like that. This stuff is beneficial to know and remember. The more well-rounded you are in what you know, the more you can set yourself apart in job interviews. You know, because when you're trying to go into commercial construction, a lot of people have construction experience. A lot of people can do estimating and takeoffs and stuff like that. But, you know, when you can set yourself apart with and impress your interviewers with information that maybe they don't know, you know, that's one way to set yourself apart. So, so again, you know, this is pretty time consuming. So, you know, early on, experts come in and do this stuff. You could do it in a spreadsheet, but this is going to be very site specific. So, you know, experts have come in and figured this out and got this equation that we can use to apply everywhere. This applies everywhere. So, you know, that's the background for what heating degree days is trying to do. We're trying to quantify energy use based on climate. Heating degree days are units are temperature difference times 1 day. So this basically says that this average temperature difference is constant for 1 day, and heating degree days is the sum for all days of the year. If you see it in hours, again, it's doing the same thing. So, you know, we've got experts that have come up with this equation that can be used everywhere. And then we have this single number that everyone that's doing this understands, that quantifies how much energy we can expect to use according to what climate we're in. So does that make sense to everybody? Was that, I know it's not the most interesting thing in the world unless you're a nerd, but it is important that you guys do understand this stuff. Does anybody have any questions on that? Okay, cool. Got a lively bunch this morning. You guys amped to be in class on this Wednesday morning? Are you super stoked to be here? Yeah, I see some head nods. I like that. That's good. A+ for you. Just kidding. All right, moving on. So here we're looking at how buildings actually consume energy based on building types. I've got commercial end uses in the US, residential end uses in the US, and then commercial end uses in the EU and residential end uses in the EU. And you notice some pretty big differences here, right? So, you know, they note that the EU has a much higher percentage for heating. So this could be due to several reasons. The biggest reason is likely because the EU is much further north than a lot of the US is. Another reason, the building spaces could be smaller in terms of floor area per person, right? Their buildings are more compact. They live closer together. They live closer to one another. They're on top of one another in some scenarios. So this is going to affect how much lighting, water heating, cooking, and cooling they might need. You know, as cultures and buildings are different, the energy use breakdown is going to change. It's difficult to understand this picture with only percentages. Something that might help us to understand this would be the total energy consumed along with these percentages. So this isn't an apples to apples comparison per se, but it gives us an idea of where their energy is going in relation to their picture. So for both residential and commercial buildings, notice in the US, HVAC is a very substantial portion of the energy budget. So upwards of 40 to 50% of our energy in buildings is HVAC. You know, we've got space heating, we have space cooling, and we have ventilation. That's a big chunk of our energy budget right there. I think that's a quiz question. So if you're half asleep, wake up. So, and you know, residential, when you get into residential, water heating comes into play there. You have different schedules and different setups and stuff like that. If you look at charts like this from the early to mid 2000s, you'll notice that lighting has dropped from around 21% to like 10%. Why is this? Well, LEDs. When LEDs became financially viable, the industry moved pretty quickly on that to start saving some money on their lighting bills. But, you know, again, it goes back to the building as a system. You have to think about how things are going to change, what's affected when you make these big changes. Incandescent lights are like little radiators. They give off a lot of heat, right? So in the winter, that adds to your heating capacity, you know, and it can be a substantial amount depending on how you design the lighting in your building. In the summer, it adds to your cooling load, right? So you're giving off energy from these lights. You're putting heat into the space, an additional heat load. So you're going to have to work harder to cool that space. So, you know, there's a trade-off when you switch to LEDs, but you know, the savings are definitely worth it. But you know, again, we're always thinking about our buildings as a system, right? So moving on. So this is a breakdown for a typical 2,200 square foot, 3-bedroom home. And remember, we're making a lot of assumptions to get these numbers, to have sort of a generalized way of looking at it, and a way that we can apply this. So again, one of the biggest places is space heating. And you've got a range here that's based on temperatures in different climates. So, you know, depends heavily on climate. You know, you could be using 5,000 kilowatt hours per year, or 25,000. You know, if you're living in Texas, you don't have to heat quite as much. But if you're living in upstate New York or something like that, you're going to have a much larger heating load, and use more energy in heating your home. And remember that heating and cooling are not always inversely impacted by climate. If you go somewhere like Iowa, it can be cold in the winter, but it can also be really hot in the summer. So just because you have a high heating bill doesn't mean you're going to have a low cooling bill. So that's something else to take into consideration. So again, cooling and heating are the two big ones here. So the next thing is going to be domestic hot water. This depends a little bit on climate. Like, where's your water heater? Is it in your crawl space? Is it in an unfinished garage, or a basement or something like that? So again, you know, all these things depend on climate. And again, you have this range of energy uses depending on where your water heater is, stuff like that. So appliances, not really affected by the climate. One of the biggest users is an electric resistance dryer. They have ventless dryers now that work off of the refrigeration cycle. Either way, the dryer is going to affect the HVAC system though. So if you have a normal dryer, you're going to be pulling air from inside of your house, heating it up, and then dumping it outside. Ventless dryers are more closed off, but they can also elevate the humidity if they're not as well sealed. They can elevate the humidity levels in the room in which they're located. So think about that. You might need some sort of a dehumidification, an additional dehumidification, or you know, it could be adding to your dehumidification load if they're not sealed very well. So that's something to take into consideration with the airflows in your house, stuff like that. So it might be a little bit more humid in your laundry room if you have one of these ventless dryers. And then we have miscellaneous electrical loads, plug loads. We've got computers and TVs, etc. So lighting, you know, if the high marks, probably incandescent bulbs. LEDs are expensive, right? CFLs are not quite as expensive. They're not quite as energy efficient as LEDs. So you know, your typical electrical consumption, you know, can vary depending on how many combustion appliances you have. For a typical house that has combustion appliances, you might see something in the range of 12,000 kilowatt hours per year. But in terms of net zero, we're going to want to be all electric. So another look at how buildings use energy and how this has happened over time. On the y-axis here, you have energy in millions of BTUs per household. So you're pretty high up here. This is in millions of BTUs per household. And remember that's our unit, MMBTU per household. So at 80 million, that's pretty high. So comparing this energy use in kilowatt hours per year, at the previous slide, we were looking at 20,000 to 35,000 kilowatt hours per year. And remember, these are both energy metrics. So BTUs, energy, kilowatt hours, energy, right? So we have total energy here. We have space heating, we have water heating, we have air conditioning, and then we have our plug loads and stuff like that. So we're looking at homes before 2000 and homes built between 2000 and 2009. So we probably have more efficient and better designed buildings between 2000 and 2009, right? And when we're looking at buildings built before 2000, we still have a fair amount of building stock that's from 40s, 50s, 60s, 70s, whatever. Air sealing levels and insulation were very, very different back then, as I'm sure a lot of you can attest to. Personally, I live in a house that was probably built in the 60s, super loose. It's insulated okay, but I've lived in some other rental houses that felt like living in a cracker box. You can stand in front of the window and feel a strong breeze, stuff like that. So these houses are constructed much differently than some of the houses that are being built today. So you might think that the new buildings would be way more efficient, right? But when we're looking at our energy use, it's sort of flat. There's not that much difference. So space heating is down, which is good. Water heating has stayed about the same. We're about the same with water heating. And now we have heat pump water heaters, which could drastically reduce this number. But they're also on-demand water heaters, but that hasn't really changed. Air conditioning has gone up, right? So that's not really great, but it's not because air conditioners are less efficient, but because more people are using air conditioners. Historically, there have not been that many air conditioners in places like Boone. But now you look at buildings being built, most of them are going to have air conditioners, right? We're sort of spoiled in a way. We're accustomed to having control over our temps in the interior of our buildings and having indoor set points with very tightly controlled and what we think of as a comfortable range, right? So we're using more energy. We have more air conditioners than we have had in the past. And again, this is one of those places where we need to sort of redefine what we think of as thermal comfort. But another thing aside from the temperatures is that our buildings are being constructed more tightly. They're more airtight. So if we don't have a means of dehumidifying, like as in in our air conditioning systems, when we're cooling, we're also dehumidifying, right? We saw that when we looked at the psychrometric chart. If we don't have a method for dehumidifying when our buildings are getting tight, we're going to run into moisture and mold problems in the summer. And again, it goes back to thinking of the building as a system. And you'll also notice that our appliances, electronics, and lighting has gone up. We have more and more electronics, right? We've got DVRs and we've got big, flat screen TVs and all of that stuff. So as we get more electronics and our plug loads increase, so too does our energy use with our plug loads increase. So the next chart is showing the percentages of households that have these things. This accounts for why there has not been a drop in energy, because more and more households have these appliances. Think back to what we were talking about with energy use at the beginning in lecture 2, with developing countries trying to increase their standard of living, and the effect that this has on energy use. As more and more households are getting more of these appliances, they're using more energy, right? So it takes energy to increase your standard of living typically. So just that's another thing to keep in mind when we're looking at this stuff. And another thing to emphasize is that we're around 90 million BTUs. So if we check those numbers, if we convert 90 million BTUs, we're going to use our train tracks method here, whatever we call it. So we want 1 million of these and 1 of these, and then we want to cancel out BTUs, right? So we got 3,412 BTUs in a kilowatt hour. And when you plug that in, you get something like 26,400 kilowatt hours. So before we were looking at a range of 20,000 to 35,000. So that's right there in the middle, 26,400 kilowatt hours. So that checks out. Always, be cognizant when you're looking at numbers like this and you're looking at charts like this. Always think about, have an idea of what realm the numbers should be in. Always, if you're using numbers like this in a presentation or something like that, try to figure out what assumptions are made. Sometimes they'll list it on the chart itself, but sometimes, there are assumptions made that are pretty significant in terms of what you can draw from this type of information from data that's being put out there, and making broad generalizations like this. So that's something to think of, especially if for those of you who are going to grad school or something like that. You're going to be looking more and more at data and doing more presentations on stuff like that. And when you give these presentations, you're going to be asked questions like that, like what can you draw from this data, and what assumptions were made when they did this study. What was your audience? How big was your sample? How many buildings did they look at? Stuff like that. So that's important information to be aware of. So other insights as to why our energy use has sort of gone up in relation to past energy use. So the square foot per person in our homes has gone up from around 500 to 1,000 square feet per person. We're at where are we at? 1,000 something square feet per person. So buildings are either getting bigger or there are fewer people in the buildings. The average household size has dropped, and the square footage has doubled. So if we're looking at, where's our household size? So three people to 2.5 people per household, and then our square footage has doubled. So we're living in a fairly affluent society right now. We have huge homes that are sparsely occupied in relation to the rest of the world, or in relation to what we really need. So this has huge implications for our energy use. We're not just conditioning the air in occupied rooms, but we're conditioning the air in the entire house. And the house doesn't have that many people in it. So one way to make a more efficient building is to make it smaller, and we'll look at that later in some of our lectures. Which take into consideration vacation homes and stuff like that, custom woodwork in them. There's a lot of those around this area. They heat those houses. They have to heat those houses a lot of the time year round. They don't turn the heat completely off. They might turn it down and winterize the house, but they're not just, and those houses are just sitting empty and they're not going unconditioned. There's a lot of stuff tied together here with the economy, especially in this area. A lot of the economy is built off of construction and stuff like that. So it's not a super simple issue, but there are things that could be done to sort of mitigate some of our energy use. So how do we best save energy in our homes? We have an idea of how much energy is consumed. How do we design or retrofit a building, and what do we prioritize to save energy? So you can, if you go from a standard baseline, low performance house to a high performance house, putting all that thought and stuff into the details, your insulation and stuff like that, you can expect about a 50% reduction in your space heating and cooling from a normal house. So it's not just one thing though. We have to consider You know, R values in our assemblies, our wall, roof, floor, etc. Our window metrics, what kind of windows we're putting in our house, our building orientation in relation to the sun, and trying to utilize some of that free heating that the sun's radiant energy can give us. We have to think about the types of systems that we're specifying in our homes. And when we're working to reduce energy use and we're making alterations to all of these things, we have to remember the building as a system again, and think about moisture and fire risks, right? There are fire risks associated with all of these changes that we're making. So, you know, we can also, you know, we can use efficient lights everywhere. This can reduce your lighting loads by around 70% from normal. This costs a lot of money though. You go from incandescents to LEDs, you know, the cost of LEDs is coming down some, but they're still not super cheap. And then we can use efficient appliances, Energy Star or better. We can use induction ranges, stuff that works off of rapidly oscillating magnetic fields. You can set your pan down on your induction range, and that alternating magnetic field is going to excite the molecules in in whatever type of pan you have that works with your induction stove, and is going to heat that pan up and not use as much energy as a gas burner and as an electric resistance eye. You can get dishwashers that are Energy Star. Again, we can get condensing dryers, heat pump dryers. The big thing to pay attention to though here is reducing our heating and cooling loads. And, you know, we can do this by passive means, by, you know, including higher levels of insulation. It is associated with a higher upfront cost, but, you know, over the life of the building, you know, your increased insulation, stuff like that, it's not really costing you a ton of money. It'll pay itself back over time. So, you know, again, heating and cooling is impacted by the building envelope and other heat/energy sources. So, you know, what are some internal heat gains? Again, we're looking at stuff like in residential, we have refrigerators, we have televisions, we have incandescent bulbs if we haven't made that switch yet. We have computers. All of your electronics are energy users, and they give off heat, right? So they're heat gains. What's another source of internal heat gain that comes from outside? Can anybody think of anything? I talked about it today. And it's going to depend on how you design your envelope, not antelope, but depend on how you design your envelope, and what, you know, specifications you have for your fenestration and stuff like that. It's a real simple answer. Anyone?
Sunlight?
What?
Sunlight?
Yes. So, you know, these are all things that are tied together, that are going to increase our heat gain, and affect, you know, the condition inside of our building. And when we pay attention to how we specify our construction assemblies, you know, we can have operable blinds and stuff like that to keep sunlight out, and that hot afternoon sun in the summers, and, you know, have appropriately sized overhangs on our building. But then, you know, in the winter, when the sun is lower in the sky, we can utilize some of that free energy from the sun's radiation and use it to help heat our building and have high thermal mass and stuff like that, and soak up some of that energy to be re-emitted later. So that's all I've got for today.